Welcome back, everybody. We're here to discuss section 7.5 a little bit further. We've already gone through learning goal 1, in which we discussed how you find an average rate of change and how you find an instantaneous rate of change of one variable with respect to another variable. And now what we're going to learn to do is to analyze an object in motion along a straight line. Alright, now just for a quick illustration of that, we're going to pretend we have some kind of path laid out, whether it's a horizontal path, a vertical path, doesn't really matter. And we're going to have some kind of particle that's going to move along that straight line from left to right, we're going to say, for the sake of our problems. And you're going to see some various things that we can do whenever we're analyzing that motion. Now I need to remind you of a couple of things that we discussed in class today, and in the previous video in fact, about whenever you find a slope, what are the units that you're using? Alright, and what I have here is a displacement graph. I don't really have the graph, so to speak, but let's pretend I had a curve right there. If I were to try to find the slope of a tangent at any point on that graph, the instantaneous rate of change, that instantaneous rate of change will be measured in meters per second, because it will tell you how many meters you changed over a certain period of time. And so we had said earlier then that since for a displacement graph the slope gives you meters per second, that the derivative of displacement is velocity. Alright, velocity is the derivative of displacement. Now I want to take that a step further. I've got a velocity graph right here. And so if we were to try to find the slope or the rate of change in this velocity graph, the units would be measured in meters per second, which is the same thing as meters per second squared. And we determined that when something is measured in meters per second squared, it's an acceleration. So just as velocity is a derivative of displacement, it turns out that acceleration is a derivative of velocity. And so here's the chain of thought that we need to have in mind as we analyze a motion of a particle in a line. All right, I want to kind of string those last two thoughts together. Since velocity is the derivative of displacement and acceleration is the derivative of velocity, then if I define a displacement function s of t, right, model of displacement, I can use that displacement function to find a velocity if I take the first derivative. S prime of t will give me the velocity of that particle that's in motion at a given time t. And if I take the derivative of the first derivative, I get the second derivative. So whenever I try to find acceleration by taking the derivative of velocity, I'm really finding the second derivative, s double prime, alright, of the position of the displacement function, and that second derivative is going to give me acceleration. Alright. First derivative of displacement gives you velocity, second derivative of displacement gives you acceleration. If you keep those two things in mind, it's going to help tremendously with the problems that we're working on. And let's go ahead and get into that. Okay, now a word before I really get into this problem a lot. There are going to be several parts to this problem, and it's going to take a lot of minutes to go through it. We're only going to have time for this one example within this video. And I think that a lot of what we're doing, since it's just an application of derivatives, is going to be logical to you. And so what I would like is, when you see each part of the problem, if you think you know how to do it, just go ahead and pause the video, try it, and then watch me and see if you were right. Now, of course, if you don't have any idea really what to do at a certain part, just watch me. We'll do more examples in our exercises in class tomorrow, and so you'll be able to apply it then and learn it now. Alright, here's the problem we're working on. It says that a particle moves along a line with the displacement function s of t equals t cubed minus 9t squared plus 15t plus 12. And that displacement is going to be measured in centimeters. And we're looking at a time interval starting at 0 and up. So non-negative times, which makes a lot of sense. And the first thing we're going to do is we're going to write expressions for the velocity and the acceleration of the particle at time t. Now here's one of those places where you pause to see if you can write those expressions, and then you come back in a moment and see if you did it correctly. Well, given the displacement function, we've already determined that to find the velocity, you just find the first derivative of the displacement function. And so the velocity function is simply going to be s prime of t, and that's going to be 3t squared minus 18t plus 15. And then we said that acceleration is the second derivative of displacement. So s double prime of t, which is 6t plus, or minus 18, gives us a function for finding acceleration. Now these three functions that we have here, the displacement function, the velocity function, and the acceleration function, are going to get used over and over again in the subsequent parts of this problem. Alright, let's check it out, but keep referring to these over and over and over again. Alright, the next thing I'd like us to do is to find the initial position, velocity, and acceleration for the particle. Pause now if you know how to do it. When you're told to find the initial position, velocity, or acceleration for this particle that's in motion, what that word initial is implying is that you're looking at the very beginning when no time has passed. So we're looking at when time is equal to 0. And so if we want to find its initial position, or initial displacement might be the better word to use there instead of position, we're trying to figure out what s of 0 is. Alright, well, s of 0 is going to be 0 cubed minus 9 times 0 squared plus 15t times 0, or no, sorry, 15 times 0 plus 12, and that of course is going to equal 12. Then we're going to find out what s prime of 0 is in order to figure out what the initial velocity of this particle is. And that's going to be 3 times 0 squared minus 18 times 0 plus 15, which is just going to simplify to be 15. I forgot to put the units on the displacement a moment ago, but I'll make sure I'll put my units here. The initial velocity for this particle is going to be 15 centimeters per second. Okay, now it's important to note here that a positive velocity indicates that the particle is moving to the right. Had the velocity been negative, it would have meant that the particle is moving to the left. Alright, and then finally, to find the initial acceleration, we're going to find out what s double prime of 0 is. And that's simply going to be 6 times 0 minus 18, or negative 18 centimeters per second squared. Sorry about that long delay there. I thought I had paused the video on my end and I noticed the time was still going. So a little bit of silence there. Okay, now I want to discuss something pretty important here. I mentioned on the last calculation that since the velocity was positive, that the particle was moving to the right. What we're going to need to work through later on in this problem, and we'll go and talk about it now, is how do the signs of the velocity and the acceleration work with one another, because the acceleration here was negative. And basically here's how it works. If for a given time, in this case 0, the velocity and the acceleration have opposite signs, that's going to indicate that the particle is slowing down at that moment in time. And if they had had the same sign, if they had both been positive or both been negative, that would mean that the particle is speeding up at that moment in time. Alright, that'll come back later on. Let's check out part C of this question. And in part C of this question, we're going to find out when the particle is at rest. If you know how to find out when the particle is at rest, pause this, figure it out. Okay, if the particle is at rest, what that indicates to you is that the velocity at that moment in time is 0 centimeters per second. Now, it's not moving, it's at rest. And so, in order to find out when the particle is at rest, we're going to have to set our velocity function, or s prime of t, equal to 0. And then solve, find out what time values give you that velocity. So let's do that then. We're going to have 3t squared minus 18t plus 15 equals 0. I'm going to make this equation a little simpler by dividing out the common factor 3, and that's going to give me t squared minus 6t plus 5 equals 0. And it turns out this is a factorable expression. We can just write this as t minus 5 times t minus 1 equals 0. And what we're finding out then is that when the time is either 5 seconds or when the time is 1 second, the particle is at rest at each of those moments in time. Alright, let's try the next part of this. And this part is telling us to find when the velocity of the particle is constant. Now, the velocity being constant is not the same as the particle being at rest. The velocity could be 5 centimeters per second, or it could be 10 meters per second and just staying there. What it means when the velocity is constant is that the acceleration is equal to 0. It's not accelerating, it's not decelerating at that point in time. And so when we find when the velocity of the particle is constant, what we're really finding out is when is s double prime of t equal to 0. So when is 6t minus 18 equal to 0? Well, quite simply, that's going to be at the 3-second mark of this motion. Alright, one last question to go through. And it's actually a bit of a doozy here. What we're going to do now is we're going to find the intervals for which the particle is speeding up and slowing down. Now I'm going to mark a few important things on these two number lines that you see right here, in which what we're going to do is we're going to consider the signs of the velocity, and by that I mean when is the velocity positive, when is the velocity negative. And we're also going to look at the signs of acceleration. And as I discussed in an earlier slide, we're basically going to find out when does the velocity and the acceleration have the same sign, and when do they have opposite signs. The particle will be speeding up anywhere velocity and acceleration are both positive or both negative, and the particle will be slowing down anytime one of those is positive and the other one is negative. You're going to have to do a lot of work on your calculator to follow along with what I'm doing right here. Okay, now I've marked on my timelines here the important key points for the velocity function and for the acceleration function. I put 0 because that was the initial time. I put that on both lines. And then I picked 1 and 5 on the velocity line because those were the times when the particle is at rest. Okay? Now, if the particle is moving to the right and then suddenly it changes to the left, it has to come to rest first. So before the sign of velocity can change from positive to negative or vice versa, it has to come to rest. And so what we're going to do is we're going to try to consider what is the speed of the particle, what's the velocity of the particle between the points at when it's rest. So what's the sign between 0 and 1 second, at what's the sign between 1 and 5 seconds, and then what's the sign after 5 seconds as well. And in order to do that, you just got to pick some number in the interval. From 0 to 1, let's say you pick 0.5. And listen to me carefully. What I want you to do is figure out what S prime of 0.5 is. Well, it turns out that S prime of 0.5 is going to give you a positive value. Between 0 seconds and 1 second, the velocity is positive. Alright? Then the particle is going to come to rest at 1 second. Now, once it comes to rest, it can either change to where it has a negative velocity, it's going left, or it could once again begin going to the right. So we need to check some value between 1 and 5, find out what the sign of the velocity is. And let's just say we choose 3. What I'd like you to do is find out what S prime of 3 is. Well, S prime of 3, it turns out, is negative. And then the particle is going to come to the rest at 5 second mark, and then it's either going to continue going left or it's going to change back to the right. Pick some value like 6 and find out what S prime of 6 is, and what you'll find is that the velocity is positive again once we get past the 5 second mark. And since the particle doesn't come to rest again, it's always going to be moving to the right from here on out. Now for acceleration, if the particle is going to go from speeding up to slowing down, it has to reach a constant speed at some point in that process. And so I put the 3 seconds here because that was the amount of time that was the time marker where the velocity was constant. And what we're going to do is we're going to look on the interval from 0 seconds to 3 seconds, and we're going to see what is the sign of the acceleration there. Is it positive or negative? And simply we'll do that by plugging in some number between 0 and 3 into S double prime. So go ahead and figure out what S double prime, say, of 1 is. Well, turns out that's negative. Alright, we'll talk about whether that means slowing down or speeding up here in a moment. Then, when we get to 3 seconds, the particle comes to rest. It could then have a positive acceleration or a negative acceleration afterwards. It turns out, though, that it does have a positive acceleration. Alright, now I'm going to put a few more negative signs here, a few more positive signs right there, and I think you'll understand why. What I need to do next is I need to compare the signs of the velocity with the signs of the acceleration and see when are they the same, when are they different. Now, look at the interval from 0 second on down to 1 second. Let me get a different color here so I can kind of illustrate this. If we look at this interval right here, you see that the velocity was positive and the acceleration was negative. So in the interval from 0 to 1, the particle was slowing down because the velocity and acceleration had opposite signs. Then if you look at the interval between 1 second and 3 seconds, okay, both the acceleration and the velocity were negative, which means that from 1 to 3, now I included 1 in the previous interval, I shouldn't have actually, it wasn't slowing down then. We're going to go from 1 to 3 here. That means it was speeding up. Alright, then if you look at the interval between 3 and 5 seconds, well, the acceleration had a positive sign, the velocity had a negative sign. So from 3 to 5, it was slowing down again because there were opposite signs. And then once we get past the 5 second mark, both the acceleration and the velocity are positive. So from 5 to infinity, it's speeding up. That's how you analyze the motion of a particle on a line. We'll do many more examples tomorrow. Hope you got a pretty good understanding of this. Thanks for watching. See you in class.